Now, to get the net positive suction head available, we have this equation. So, net positive suction available, so it is equal to the suction pressure. Suction pressure, your PS, so we have your PS, so at this part, so at the suction pipe of the pump. Now, that is divided by the specific weight, so that is given by the density times the gravity, which is equal to 1000 kg per cubic meter times the 9.81. So but we have 9,810, that would be Newton per cubic meter, then plus the velocity at 0.1 square, so that will be the suction velocity. V1 stands for the pump suction velocity, so this will be our 0.1 at this point at the suction. Then it is raised to square, then divided by 2 times the gravity, which is 9.81, minus PB, which is the partial pressure of the fluid at a given temperature in the unit of Pascal, then divided by the specific weight of the liquid. So it can also be expressed on net positive suction head, so it can be also expressed as the atmospheric pressure divided by the specific weight minus Z1. So Z1 stands for the elevation of the pump from the liquid. So elevation 1 is from the surface of the liquid to the reference line of your pump. So that will be the distance at the reference line. So in the middle of the pipe going down to the surface of the water that is being pumped. So I will adjust this 0.1. So 0.1 will be given at this part. So I'm adjusting that 1. So let's clear that one. So correction, this is our 0.1. So since we don't have given initially for the pressure at the suction, we'll try to derive that one on the from the given velocity triangle to get the value of your pressure suction. Now I bring down here the blade impeller of the pump, so this one, okay. So looking at this side, okay, if you're going to do a section here, you will see at this portion of this surface of the pump impeller. Now by applying the Bernoulli's equation inside pump points 1 and 2, so we can write that our pressure at the suction, so that will be divided by, so that will be divided by the specific weight of the fluid. So we have the specific weight of the fluid, then we're going to add our velocity at 0.1, so square, then we shall divide this one by 2 times the gravity plus the elevation at 0.1, or the reference at this point. Then we have your pressure 2, which is at the discharge, or the discharge of the pump. So it is also divided by the specific weight of the fluid plus the velocity at 0.2 squared, then divided by again by 2 times the gravity plus the Z2, or the elevation of the discharge line, then minus your head. Now to get the head developed by the pump, we just simply rewrite our equation as your head, which is now equal to the pressure 2 minus your pressure at the suction, then divided by the specific weight So that will be plus also the velocity 2 at point 2 square minus the velocity 1 square, then divided by 2 times your gravity, so plus Z2 or the elevation at point 2 divided by your say 1. Minus say 1. So this is now the head developed by the pump. The change in elevation Z2 and your Z1 can be eliminated due to a smaller value. So we can rewrite our equation, your head, as that will be now equal to H is equal now to your pressure 2 minus your pressure at the suction divided by the specific weight, then plus the velocity 2 at point 2 square minus your velocity 1 at point 1 square, then divided by 2 times your gravities, so Z will be eliminated due to smaller values, and we can factor out from the equation. So we can factor out from our equation the T. So this one can be expressed. So I can express this specific weight. So I'm gonna change this one as density times the gravity. So I can factor out the gravity 1 over G. So what is left now is your pressure 2 minus your pressure suction divided by the density, then plus your velocity 2 squared minus your velocity 1, that will be squared, then divided by 2, then shall we close parenthesis on this one, and we can transpose our we can transpose our G here. So we have your HG, that will be head times the gravity, and we have what is left is the pressure 2 minus your pressure suction divided by their density plus our velocity at point 2 squared minus your velocity 1 squared, then divided by 2. And we can express the pressure or the change in pressure 2 minus your pressure at the suction. So this is divided by your density, can be expressed as your head times your gravity minus your velocity 2 at point 2 squared minus your velocity 1 at point 1 squared, then divided by your 2. Now we can transpose our density on the other side, so we can rewrite our equation. So we have your pressure 2 minus your pressure suction, so that will be density times the head times the gravity minus density, so that will be multiplied by density, then we have your velocity 2 squared minus your velocity 1 squared, okay, and it is divided by all over by 2. Now to get the pressure of the suction, so we can transpose this one, so we can now rewrite that our equation as we have your pressure suction, so that will be equal to pressure 0.2, so that will be minus density, the head times the gravity, so this will be plus. Now we have plus, we have your density multiplied to velocity 2, so that will be raised to squared minus your velocity 1 raised to squared, okay, then divided by 2. So we have here the equation to get the pressure at the suction, Ts. So for pressure 2, so we have here, for example, if you have a pressure gauge here, so we can determine what will be the given pressure. But for now, in order for us to get the value of the suction pressure, so there must be a pressure 2, and we can also solve the velocity 2 and velocity 1 here. So by combining that one, so we can arrive to get the value of the pressure at the suction, so that we can use to determine the net positive suction available on the based on the installation that of the setup.